In this sheet, we're going to talk about how you apply the hypothesis testing procedure using the t-distribution. When we're doing a hypothesis test for the mean, it's more often in real life that you won't actually know the population standard deviation. In the hypothesis testing procedure, we're trying to see if an estimate for the population mean is reasonable using the sample data. So usually if you only have the sample data, the standard deviation that you have is S. When the standard deviation that you have is S, the sample standard deviation, then this part on the bottom of the fraction here is called the standard error of estimate. When you have the standard error, that's a second value that you have to estimate. And when that happens, we get what's called the t-distribution instead of the normal distribution. The t-distribution is very similar to the normal distribution. The main things about it are that it is thicker in the tails than the normal distribution. That means it just doesn't like fall as quickly. So for example, if this was the normal distribution, the t-distribution would be thicker in the tail, so it would come out a bit slower, for example. Also, the biggest difference with the t-distribution is that it changes according to the size of the sample. It has what are called the degrees of freedom that are calculated as n minus 1, the sample size minus 1, and all that means is that the shape changes slightly depending on how many people are in the sample. So the t-distribution must be used when we're talking about the mean when you only have the sample standard deviation S, and it's especially important when n is small. The reason it's especially important when n is small is because if the sample size is small, the t-distribution will be more different than the normal distribution. But if the sample size n is very big, then the t-distribution and the normal distribution are almost identical. So it actually won't make much of a difference if you use the formulas we're going to learn in this lesson or the ones that we learned in the last video on the normal distribution. So if these 3 points are met, that's when we need to use the t formulas. The formula for the test statistic has the same format as the ones when we learned in the normal distribution video, except that we've changed from the population standard deviation to the sample standard deviation. What has the biggest difference is the formulas for the p-value and the critical value. The reason these ones have the biggest difference is because the t-distribution in Excel doesn't just work like the normal one, where the normal distribution for norm.s.dist and norm.s.inv, they always give you a less than probability. So whatever probability you put in there or whatever score you put in there, it's always less than the value. However, for the t-distribution, when you use like t.dist, there are 3 different options. You can use the lower probability, that's the less than. The one called RT is for right tail. That actually gives you the greater than probability, so you don't have to do 1 minus. And you've also got one called t.dis.2t that gives you what's called the two-tailed probability. So it'll give you what's on the ends here without you having to cut it in half or do 1 minus again for the other side, positive versus negative. So because it has these 3 options, you won't have to worry about, like I said, 1 minusing for the values or the alpha so that you can get all 3 options for a right-tailed test, a left-tailed test, and a not equal to test. For p-values, we use t.dist. Which t.dist you use depends on what type of test you're using. RT for right-tailed test, just regular t-dist for lower or left, and 2t for two-tailed. Then for critical values, use t.inv for both the lower and the upper test. The reason that those only use the one function is because there is no RT or right-tailed option. Those are both considered what are called one-sided tests, meaning they're just on one side of the curve. So if you want the upper value, you do have to do 1 minus for the critical value, and the two-tailed option will still be .2t for that two-tailed option. Other than that, the hypothesis testing procedure stays the same. So we can give an example a try using these t distribution formulas in Excel. So our first example is on battery life. We saw this example before in the confidence interval lesson, but now we're doing a question about hypothesis testing. We want to do a test to say that this company has a goal of developing batteries that last more than 300 minutes. They test 12 of them and they get these lifespans with a sample mean of 306.25 and a sample standard deviation of 29.31. Is there evidence the company's met its goal at the 0.05 level of significance? And because we've done this problem before, I say assume the conditions of hypothesis testing are met, so we don't have to keep checking those conditions. So, step one of the hypothesis testing procedure, always your null and alternative. Because we're talking about the mean, I'll start with my parameter mu, and the null always has the equal sign. For the null, we'll look at the goal the company has, which is 300 minutes in continuous use. That doesn't mean the battery life is 300 minutes, that is just their goal. They want to prove that the batteries can last more than that. So we're trying to see if they are more than 300 because when they did a sample of 12 batteries, they got just over that, 306.25. For the sample mean, you could just write 306.25, but if you want it very precisely, you could actually take the individual data points for each of the tests for how many minutes they lasted and do the average. The population goal is 300 minutes and the number of batteries is 12. For the sample standard deviation, again, this is only for 12 batteries, not for the full population. So because this is sample data and not population data, and also because 12 batteries, N is very small, small sample means you have to use the t distribution. When you're using the t-distribution, we calculate the t-test statistic by taking our sample value minus our population hypothesized value and divide by what's called the standard error instead of the deviation. Again, it's called the standard error because, oh, it's messing up because it thinks I'm clicking on that circle, but there we go. I had to get the correct cell reference, but it's called the standard error because we use the sample standard deviation instead of the population one, and that's why we have to use the t-distribution. To calculate the p-value, you have to think about what type of test you're doing. For the type of test, always look at the direction in the alternative. The population goal is 300 minutes, but in the sample, we got 306.25 minutes, which is greater than that. So the alternative has the greater than symbol. Because the alternative has the greater than symbol, we're trying to find the probability of being greater than. That's our p-value. And it's on the right or upper side of the distribution, which means if you want to find that probability, you should use t.dist.rt. You could technically just use t.dist, but then you'd have to do 1 minus to get the upper instead of the lower probability. The first thing you put in is your value for t. The second thing you have to put in is your value for the sample size. And again, I just have to be careful with where I click because of that drawing on top. But it will be the sample size minus 1 because the t-distribution values change as the sample size gets bigger, it gets closer to the normal distribution. But for a small sample like this one, the value would be different than the normal distribution would give you. So the p-value is about 24%. We're testing at 5%, so our rule for rejecting the null hypothesis is that the p-value has to be less than alpha, but at getting about 24%, that p-value is definitely greater than alpha. So our decision should be do not reject the null hypothesis in this case. If you wanted to use critical values instead, critical value should get you the same answer. The critical value, we'll call it T star now instead of Z star because we're working with the T distribution. And it's that cutoff point, that 5%, which is your level of significance. What would be the cutoff that any point beyond that we call an outlier? To get the T star value, I use T dot in. There's no RT option for the T dot in function. So I do my regular way and do 1 minus when I want the upper or positive value. Whoops. And I still have to put in my N minus 1, which is an H34, to get the degrees of freedom for the distribution. And that gives me about 1.796. So the cutoff value for where we would reject the null hypothesis, or what we call the rejection region, is at about 1.79 when our t-test value for the 306 is only 0.74. So because 1.79 is so much bigger than 1.74, the 1.74 is not within the rejection region. What I mean by that is it's not more extreme than the point in red where you would be able to reject based on the critical value. So again, using the critical value because t-test ends up being less than our t-star value, that also is a reason to not reject. T-test needs to be bigger than t-star in order to say you reject. And in this case, it's smaller. So because we got do not reject the null hypothesis, what that means is that we have to stay with the null. We keep this and we believe this to be true because we have not proven otherwise. So what this means is there is no evidence that the company has met its goal to increase battery life to over 300 minutes. So it hasn't proven that it's over 300. We're assuming it's equal to 300. Using this hypothesis testing procedure, we have a probability associated with getting the sample results, and it's not considered unusual enough. So again, another way of saying this is if the battery life was exactly equal to 300, it's possible to get a random sample of only 12 batteries where the battery life was actually 306.25. That actually would happen about 24% of the time. That's what your p-value says, about 24% of the time. 24% is quite frequently, or it's not considered weird enough. Anything less than 5% we consider too weird, that it does not happen very likely or very often. 24% is too big. So that's why we do not reject the null hypothesis and we say 306.25 is too close to 300. They have not proven that it's actually a significant difference to prove above 300. That's just another way to think about this question. I have another one for you here, so that we can try all the different directions of the test. This one says the cost of a daily newspaper varies from city to city. A study was done to test the claim that the mean cost of a daily newspaper is $1. 12 papers purchased yield a mean cost of 95 cents with a standard deviation of 18 cents. Do the data support the claim at the 1% level? So step one is I'm going to write my null and alternative. This is about the mean or average cost of a newspaper, so I'm going to use my population parameter mu because I'm talking about the mean and not proportions, and the null should always have the equal sign. They say that the claim is that the average cost is $1, but when they actually did a sample, they got 95 cents, which is less than that. However, this question about the data supporting the claim, it's just really asking, is it a dollar or not? With that specific wording, just saying, does it support the claim? It doesn't specifically say, is the price more or less expensive? This is where you can use a two-tailed test, just to say, is 95 cents different enough than $1? Not necessarily bigger or smaller. For the two-tailed test, it's testing if you could be bigger or smaller, where the mean amount of $1 would be in the middle, and we want to find the chance that you could be bigger or smaller than that amount. To test this, let's use the numbers from the question. The sample mean is 95 cents. Our hypothesized value is $1. We're told 12 newspapers are purchased, and from the 12 papers, the standard deviation is 18 cents. Again, because the standard deviation is 18 cents, that's a sample value, and 12 is very small sample size. That means we need to use the t-distribution instead of just the basic normal distribution. For the t-distribution, our t-test statistic can be calculated using sample value minus population value over my standard deviation divided by the square root of the sample size. You'll want to put brackets around the denominator too to make sure that it's computing it in the right order, and you get negative 0.96. What this means is that, let's say my sample value was somewhere over here at negative 0.96 as my t-test statistic. That corresponds to 95 cents. 95 cents is less than the dollar. That's why I know it's on the left. Also, a negative test statistic means you're on the left, because once you put it in the formula, the standard distribution for t or normal would be centered at 0. To actually see what the probability is of being less than the 95 cents or negative 0.96 t-test statistic, we can calculate our p-value. Technically, this was a two-tailed distribution or two-tailed test we want to conduct. So because it's a two-tailed test, I can use the .2t option. My t dot test and my degrees of freedom are n minus 1. Oh, the reason it's coming out with the num sign is because I entered a negative value for the t-test. When you want to use t.dist.2t, you have to only use the positive number. So if you use the function ABS for absolute value, it will just turn this into positive 0.96225 instead of the negative number, so that the function actually will give you an answer for the p-value. If you recognize that 95% is on the lower end, you could also just use t.dist, and then it does work for the negative value. Let me just show you what happens in that case. What happens in that case is you only get a value that is half of the p-value with t.dist.2t. So this is half of the t.dist.2t value, basically because the .2t value is giving you both ends. So what the negative and the positive would give you. Like 0 plus positive 0.96 and negative, it's adding what's in here, the p-value on this side and the p-value on this side for both tails. When you have the value in both tails, 0.356, so this and this added together instead of just one tail at a time, you can directly compare your p-value to the value of alpha, because the value of alpha would also be split between the tails for a two-tailed test. So if you use the t.dist.2t function, just remember to use absolute if you have a negative, like I had forgotten to do, so that it gave me the num error. But when you do it this way using the .2t, the benefit of doing it this way is that you can directly compare your p-value to the value of alpha. 36% is way bigger than 1%, so this would be another do not reject the null, because it's too big of a p-value. If you'd prefer to use the critical value to make a decision, again, because this is a two-tailed test, t.inv.2t, probability and degrees of freedom is what has to be put in there. And I'd get 3.105. Anything beyond 3 is typically considered an outlier, so this would be big outliers beyond 3 on either side, plus 3.1 or minus 3.1. Just to help you see the full picture of how this works, if you wanted to use just t.inv to get this answer, because alpha 0.01 should be included in both tails, if you want the number just in one tail, you'd have to cut the value of alpha in half. We did an example like this for like confidence intervals with dividing it in half, leaving it on the ends, but it gives you the same number. See how that works for the two-tailed test? Because for the two-tailed, you're technically testing upper and lower. So when we're testing at 1%, technically we're testing at 0.5%. in each end for that because it's 1% in total when you add it together. So if you use the .2t function, it will consider that cutting in half for you. If you don't use it, you have to do that manually, which is what you see for the normal distribution calculations when I told you to do alpha over 2 for the critical value. But for the t distribution, because they have this function with .2t, you don't have to divide it by 2 if you use the .2t function, or you can just use the regular tinv and then divide it by 2 just like you do for the normal distribution, if that's what you remember better. But looking at it both ways should help you to see the whole picture and how they work together. If you want to use the critical value to make a decision, the negative 1.96, or if you look at the absolute value of it. So again, don't worry about the negatives. 0.96 is definitely less than the 3.1 from the t star value. And we can only reject if t test is bigger than t star, the opposite. But in this case, t test is smaller than t star, so we do not reject. Not rejecting means we stick with the null, which means that there's no evidence that the average price is not $1. So there's no evidence that you've proven the alternative of not equal to $1. We're sticking with the null, which means that the price is about $1. There's one more that I want you to try, this learning check on insurance. Please pause the video here and actually do try it on your own to make sure that you can get the correct answer with the p-value and the critical value method, as well as your interpretation, because that will help you to prepare for the assessment. Okay, so I'm going to show you the solution now. I hope that you actually did pause the video and try it on your own, and this will verify if you got the right answers. So for this one, I'm going to start with my null and alternative. Because the question's about the mean or the average sales, the management here wants to know that the mean profit of insurance policies sold by the rep is less than 1,500. So the null always has the equal, so it'd be equal to 1,500. And what they're trying to prove is that the policies sold by the rep are actually less than 1,500. How we can prove that is by using our hypothesis testing procedure, where the sample average from the question should be 3890, sorry. The hypothesized value is 1,500 that appears in the null and alternative, and the number of policies is 30, found here. The standard deviation, 1329.60. And my t-test score will be my sample mean minus my hypothesized mean value divided by my standard deviation over the square root of n. The reason I know I need to use the t-test statistic and not the z-test statistic is again because this is a sample standard deviation. It's from the sample, only the 30 people, and the sample size of 30 is also less than 40. It's still considered pretty small. That means use the t-distribution. So for this test statistic, you can calculate the p-value. Before I do that, I'll just draw out a quick picture because that can help you if you see if you use the right function or not. So we were trying to test if you're less than 1,500. 1438.90 is less than 1,500, so I drew it on the left, and we want the probability of being less than that amount. That will be your p-value, the probability as the area under the curve. So because it's on the left, you can use t.dist by itself, not RT for right and not two-tailed for 2, because we're doing less than. That will just be the regular t.dist function where you enter the t-test value, the degrees of freedom, which are n minus 1, and cumulative should be set to true. And we get a p-value of about 40% chance of this happening. So if the real average amount of the policy was 1,500, there's about a 40% chance you could get a sample of 30, where the average is 1438.90 instead of 1500. A 40% chance of that happening is pretty likely. So specifically, if you're testing at 5% and saying only values less than 5% are the ones we reject, 40% is way bigger than the alpha. So this is another do not reject the null hypothesis. If you want to use the critical values instead, because this one is on the left, we can use t.inv just with our value of alpha. No need to cut it in half because it's not two-tailed, and no need to do 1 minus the alpha because it's already on the left and not on the right. And any value that would be lower than 1.699 on the negative side would be considered a reject, but our value is not lower than that. If we talk in absolute values, which just means ignore the negative, 0.25 is less than 1.699. And again, it's easier a lot of the time when you're talking about these to just put everything in absolute value so that you remember you can only reject if t-test is bigger than t-star. In this case, it's not bigger. So we do not reject the null. So again, because we didn't reject for this one, we're stuck with the null hypothesis, which means we believe that the averages for the policy is still about 1,500, or in other words, there's no sufficient evidence or proof that the mean profits of policies sold by this rep is less than 1,500. So another way of saying that is we did not go to the alternative hypothesis. We're keeping the null. We have not proven that the profit is less than 1,500 with the data in the sample. Okay, so we've now done 3 questions. A greater than in the alternative, a not equal to in the alternative, and a less than in the alternative using the t-distribution functions. In each of these cases, we actually got do not reject the null, so we stuck with the null hypothesis. But for the normal distribution from the last video, we did a less than question and a greater than question. And for both of those questions, the answer was reject the null hypothesis. So we had a mix of each in this lesson. Hypothesis testing can be a tricky topic, and it often takes you a couple of times seeing it before you fully can grasp the intricacies of the procedure and how they relate to confidence intervals, for example. So this is not something that you'll never touch again. You will talk about hypothesis testing more in your next course called Business Analytics next semester. So stay tuned to learn more about hypothesis testing during your Business Analytics course. Otherwise, thank you so much for watching this last lesson video for our Statistics for Business course. Please reach out if you have any questions about the content, specifically if you have questions also about the last assignment or about the upcoming exam. I'll be really happy to assist you. Have a great day. Bye.